Hello, grade 11s. I'm sorry, I miss you today. We're going to fill out this handout together before I give you some textbook questions to work on. So yesterday we talked about simple and compound interest, where simple interest is a one-time deal that you calculate the interest, often in association with Uncle Louie. Compound interest is where interest is calculated on interest. So if you are saving money, it's a good deal. If you're owing money, not so good. So we've got some compound things to look at today since it's more common. First of all, question number 1 seems like a silly thing to focus on, but could you please put a big star by this one? Because you will make a boo-boo if you're not careful, and that would be just silly. So if we're going from a percent to a decimal so that we can use these percents in calculations, we know that 25% means 25 out of 100. Or we put the 25 in the hundredths column. So basically our rule is move the decimal to the left 2 places to write it as a decimal. Be careful for this one, and it's always invisible after the percent, but this one would be 3.12, which seems kind of strange. 6.1%, the temptation is to write it as 0.61, but it is 2 places to the left. We need a 0 to hold the 1 place. Just do a quick mental check. That is very close to 6%. It fits with our original question. 2.19%, moving 2 places to the left, would be decimal 0.219. And lastly, 0.258% is so tiny, it's not even 1%. So we are moving the decimal 2 places to the left. I need 2 zeros to hold my place value. Decimal 0.0258. Be careful about those. This particular thing that I have written here is not on your handout sheet, but sometimes it can be helpful to think of it in this way. If you have $1 right now, then you could have put into your account less than $1, leave it there, and you would get your dollar in the present. If you have $1 right now and you save it, then in the future you will get greater than $1 as interest is added to it. So you have some charts as we continue to work with our interest rates. So if you are given an annual interest rate, that means yearly, at the bank of 12%, they can't give you 12% if they were to calculate your interest twice a year, or they'd go broke. So they take your 12% and they divide it by 2, which makes sense. 12% annual interest rate would be a 1% monthly interest rate. Okay, let's go with the 18%. How much would we get semi-annually if they sat down twice a year and calculated how much money is now in your account? They would do 9% both times. If it was monthly, how do I figure out that monthly interest rate? We take our 18% and we divide it by 12. Which is 1.5% every year. What if I had 2% monthly interest? What would that be semi-annually, and what would that be annually? Annually, if I've got 2% per month, it would be a 24% annual interest rate, which is a 12% semi-annual rate. So none of these calculations are big deals. We just want to get you used to the lingo. If you have an 8% semi-annual interest rate, going to an annual interest rate, we double it, 16%. What is that monthly? You get it by 16 divided by 12, or 16% divided by 12 months in a year gives somebody has a nice fraction button, it's 1 1/3% per month. 7.2% annually. So here's a more realistic with a decimal in it. 7.2% annually would be 3.6% semi-annually. And monthly would be our 7.2% divided by 12, which is not even 1% per month, 0.6%. All right, we're going to look at the second table as well. We're talking about compounding periods. Okay, the way I explain it isn't really what happens, but compounding periods to me is how many times in a year your banker sits down and figures out your interest and puts it into your account. It isn't really true. The computer does it all the time, regularly for us. But if we have a 5-year period and your interest is compounded annually, that means your banker sits down with your books 5 times total and figures out your interest. If your compounding periods are semi-annually, that means he sits down twice a year, January and June, and figures out your interest. He is going to make calculations with your bank account 10 times per year. And if he were to do it monthly, we would have 60 times in that 5-year period that he sits down and calculates your interest. If it's a 10-year total period and your banker calculates your interest annually, there will be 10 calculations. If he does it semi-annually, 20. And if he does it monthly, it would be 120 total calculations of your interest. 15 years semi-annually would be 30. 15 years monthly would be 15 years. Once every month would give us 180. If we knew that the interest was calculated 18 times and it was semi-annual compounding periods, that means that annually would be 9, which means that we have 9 years of investment. If that is monthly calculation, it would be 9 years times the 12 months, which is 108. If we have 48 compounding periods, that's once a month. That would have taken 4 years to come up with that many calculations. That means 4 annually and 8 semi-annually. It's going to make a lot more sense when we put it into context of some real world problems. All right, Carolyn's grandma gave her $1,000. She invested it for 4 years at 4% per year, compounded annually. So those numbers are all key. I find this table that we've drawn here can be helpful. How much did she have at the end of the 4th year? So year 1. Her banker sits down once a year and calculates interest, and it's compounded interest. So she gets 4% of her $1,000. So just down here, let's calculate her interest for year 1. She had $1,000, and her interest was, as a decimal, 4%. That means he's going to add 40 bucks into her account. So at the end of year 1, she has $1,040. Another way to write that is 1,000 times, well, a 1 will keep our $1,000, and 4% will add 4% to it. Year 2. He sits down with her money again. This time he's going to take $1,040 and he is going to times that by 4% and give her a new total, which is $4,160. So now she has $1,081.60. Another way to write that is our initial value times 1 for growth and 4%, and we've done it twice. Next year, he is going to calculate interest on $1,081.60 times our interest rate, which is $43.26. All right, what is that when we add it? $1,081.60 plus her new interest. $112,486. And the last year, he takes her total $112,486, gives her her 4% interest rate, is $44.99. So in her account, $116,985. I should be using different colors here. Another way of doing this is our initial value. We have growth, so we have 1 plus, interest rate is 4% from yesterday, times to the power of 3. 1,001 plus decimal 04 to the power of 4. It's compounded interest, and our equation is exponential growth. So we don't have to draw a table of values. We could just type this equation in to get our final answer for the end of that pay period. From that example, and from the fact that we understand exponential equations, we can write an equation with letters that can be helpful to encourage us to remember what our equation stands for. So an exponential equation. We start with initial value. Our initial value in money problems we call P. Just like in the simple interest problem, that is your principal. With exponential equations, we would then do a rate of growth. So that would be the base of our power. And this will be 1 plus, because it's rate of growth, I for interest rate. And that should be as a decimal. And lastly, if it's exponential growth, then we have to have an exponent. We will do n for number of years. So nothing new. We're just using letters that help us to remember what we're looking for. This would be A for amount of money. So for this one, for instance, we could use the amount is the principal times 1 plus the interest rate as a decimal, decimal 04, to the power of n number of years, 4. And our final answer would be 1,169.85. The next example you have is about Mark. Mark borrows $3,000. Okay, so this is borrows, so this is sad. He borrows $3,000 at an interest rate of 4.75% per annum, compounded annually. He plans to pay back the loan in 5 years. How much will Mark owe after 5 years? Most often when we take a loan, we pay it back bit by bit. But this guy is going to take a loan and not touch it for 5 years and then pay it all back. Let's see how much he owes. So our equation was the amount of money is the principal, 1 plus the interest to the number of years. So he borrowed $3,000. His interest rate is 4.75%, so we've got to change that to a decimal. So 2 places to the left would be decimal 0.475 to the power of 5 years. It would be really great if you would just pause for a second and make sure that you can enter this into your own calculator correctly. We would end up with $3,783.48. So it costs him $783.48 to have that loan for 5 years. How much interest will he pay? The interest is the total owing, subtract what you actually borrowed, is $783.48. Okay, last question is going to refer to those tables that we filled out on the front page, because this one is going to be a little bit more real life, a little bit more difficult. Sophie put $2,500 into an RRSP that earns 7.5% per annum. Determine the amount of the investment after 8 years if A, the interest is compounded annually. So this will be the nice one to start with. So how much money does Sophie have if she had $2,500? Initial value, $2,500. 1 plus the interest rate as a decimal. 1 plus. Interest rate is 7.5%, so decimal 0.75. And the number of years is 8. So for this one, because it is compounded annually, our banker sits down once every year, calculates the interest. This is what we get. And that total, this is a little stunning, but it's $4,458.69. B, the only thing that changes is that the interest is compounded semi-annually. If you go back to the table at the front, then 2 things change. If it is semi-annually, then the number of compounding periods change. N is no longer just 8 years, but it's 16 calculations. So twice a year, 16 times they're going to figure out your interest. It also changes your interest. If you have 7.5% per year, they're going to give you half of that every semi-annual calculation. So your interest is no longer decimal 0.75, it's 7.5% cut in half. So that's 3.75%. I just divided 7.5 by 2, which as a decimal would be decimal 0.375. So 2 things change. So for B, our amount, we invested $2,500. It's going to get a semi-annual rate of decimal 0.375, but it's going to be calculated 16 times. What's your guess? Is that going to be better for her or worse? Let's type it in. And again, it would be really good for you to pause this and use your own calculator. $4,505.57. So based on one example only, it appears that the more often your money is compounded, the better it is if you're the one saving. If you're borrowing, not so much. Okay, let's try C, and I'm going to use angry red. The only thing that's changed is the compounding period. So it is now monthly. That means instead of calculating my interest 8 times or 16 times, it is 8 years every month. So the N value that I'm going to use is 8 times 12, which is 96. My interest rate also is different. It's 7.5% per annum, but I want to know what that is as a monthly interest rate. So I am going to do my 7.5% and cut it by 12, which will give me not even 1% per month. It's 0.625%, which as a decimal is, move it twice to the left, decimal 0.0625. So we have some things to watch out for. We have to be very careful that our decimal is in the right place and that we have watched our compounding periods. It changes two things, the N and the I. Let's calculate and see if this is better for her. That's my prediction. The more often it's compounded, the more money you make. 2,500, 1 plus decimal 0.0625, and it is compounded 96 times. 2,500. Type it in as you see it and make sure that your calculator is your friend. To the power of 96. Here we go. 4,546 and 80 cents. Remember, it's money, so we round to 2 decimal places. So it is much better for her the more often it is compounded. Sorry, just had a coughing fit. Please try some textbook questions. Page 468. Number 3, 5 to 8, and 12.